Okay, we'll get going today with the last new stuff that we're going to cover, believe it or not. So on Monday, I'll have sort of some review things that I think are things that we should go over, which in my estimation were the ones that we need to review. But if you have anything else last minute you want me to cover, just let me know. I can make some last minute changes to that. There will also be the exam review today for exam 3. Alright, so don't forget about that. And then all of the final exam reviews will be done in class starting on Wednesday through the last Monday of class, so Wednesday, Friday, Monday. Alright, so today we're going to do, like I said, the last bit of new material, which deals a little bit more with phase changes. So the first thing we're going to talk about are what are called heating curves. So we've talked about how to calculate heat for physical processes using that MC delta T equation. Now that only applies to if you have one phase. What happens if we go through multiple phases of matter? So let's say we start with ice, which we know is solid water, and we're going to heat it at a constant rate. So what I'm showing here in this plot is this is going to be the temperature in degrees Celsius, and what happens to that temperature as we add heat to it, going from left to right. So if we start at minus 20 degrees Celsius, we should recognize that the freezing point of water is 0, so that means we're going to be in the solid phase with ice. So we're starting at minus 20. And as we add heat to the ice, the temperature is going to increase. Remember, as we add heat to something, the temperature increases, and that's going to happen until we get to the first phase change point, which is 0 Celsius. So this first part here, as we add heat, we're going to increase the temperature, and that's going to be the ice part of our curve. But then once we get to 0 degrees Celsius, we know that we're at the melting point of water, and so that phase change is going to occur. And as the phase changes from ice to water, from solid to liquid, the temperature is going to remain constant. So one of the key concepts we need to talk about now is that as you're adding heat to a substance and it's changing its phase, the temperature remains constant during the phase change. So at 0 degrees Celsius, we're going to put in some more heat, which is going to cause the phase change to happen. So at this stage, when we're at 0, we're going to have a mixture of ice and water. And we're going to add more heat to this until all of the ice converts into water. Okay, and then at that stage, we're going to start heating the water again. So now we have liquid water at 0 degrees Celsius. And as we heat that up, it's going to increase its temperature all the way to 100, which is the next phase change. So liquid water exists between 0 Celsius and 100 Celsius. So during that temperature range, as we add heat to it, it's going to increase the temperature in a kind of linear relationship because heat is MC delta T, linearly related. And so during this temperature range, 0 to 100, we have water with the temperature steadily increasing. Once we get to 100 degrees Celsius, we're now at the next phase change point, which is the boiling point of water going from liquid to vapor. And so at this stage, again, the temperature is going to remain constant as we add more heat and convert all of the water into vapor, or steam as we call it for water specifically. So at this point we have a mixture of water and steam, and again, as we add heat to that mixture, we're going to keep the temperature constant until all of the water is converted into steam. And then finally, once we have gas phase water, which we call steam, we can continue to heat that up even further if we wanted to as well. So as we add more heat to the system, the steam is going to go from 100 degrees Celsius, where it first converts into steam, and then raise from there. So this is kind of a qualitative diagram of what it looks like when we heat up a substance and it involves two phase changes where the temperature remains constant as those phases change. Now the question becomes, how do we calculate the heat that's added or the heat that's associated with each of these transitions here? So, the heat for going from from minus 20 to 0, the heat that's associated with ice and water, the heat that's associated with heating the water, all these terms and add them together get the total amount of heat that's added, and we can do that using some concepts that we should already know. All right, so we're going to do just an example of this. We're starting with 5 grams of ice at minus 20 degrees Celsius, and we're going to heat it until it reaches the gas phase with a temperature of 140. So that's kind of what we showed here. We're starting at minus 20, we're ending up at 140 degrees Celsius, but we know that we have to go through a couple of phase changes in the process. So how do we calculate the total heat that's associated with that process? So we're going to divide it up into the different phases, or the different segments, I guess you will. All right, so segment 1, I won't use the word phase because that'll confuse us when we talk about phase changes. So segment 1 of this process is going to be, as we showed, We're going to warm the ice from minus 20 degrees Celsius, which is what we're starting at, to the phase change temperature, which is 0 degrees Celsius. Now, if this was something besides water, we would have to tell you what that temperature is. We're not going to expect you to memorize freezing points and boiling points. But for water, you should know that it's 0 degrees for freezing, 100 degrees for boiling. That's kind of how the Celsius scale was designed in the first place. All right, so that's going to be the first segment, is warming the ice from minus 20 to 0 before the first phase changes. And anytime we're within a certain phase, we calculate heat the same way we did before. Q is equal to mc delta T. But one thing we have to realize is that this heat capacity is dependent on the phase. So solid phase ice is going to have a different heat capacity than liquid water, which is the one that we've always used, 4.184, and that's going to be different from gas phase water. So we gave you all those values here. Heat capacity for the solid is 2.09, the liquid is 4.18, and the gas is 2.00. Sort of just a coincidence that the first and the last one are similar, and that's not always the case. But at any point, we go mc delta T for this first transition. We have 5 grams of ice. The heat capacity for the solid ice is 2.09. We have to use the correct value. And we're warming it by 20 degrees Celsius or 20 Kelvin, going from minus 20 to 0, which is delta T. So that's going to be 209 joules. We're going to end up calculating our answer in kilojoules, although I didn't specify that, but so we'll keep in mind that that's 0.209 kilojoules. Okay? So that's the first segment, warming the ice from minus 20 to 0. So in that, it's just mc delta T. Now for the second segment, which is going to be melting the ice, how do we calculate the heat that's associated with a phase change? So for that, we're going to use the associated phase change enthalpy, in this case the delta H of fusion, the second number here. So remember, fusion refers to the heat change associated with melting a substance, delta H for that process. And so to do that, we're going to take, the heat is going to be the moles of ice times delta H of fusion. Okay, because these phase change enthalpies are always kilojoules per mole, so we have to take the moles of ice that we have and multiply it by that number to get the total amount of heat that's associated with melting 5 grams of ice. So we have to convert grams to moles. So for these segments, we're going to need the moles of water whenever we're doing phase changes, because those enthalpies are per mole. So we have 5 grams. We just divide by the molar mass, which is the same for all three phases, of course, 18.02. And so we have 0.278 moles of water. So that's going to be the amount of water we use when we're using the molar enthalpies of fusion and vaporization. All right, so for this, we take that number, which is 0.278 moles, and we multiply it by the enthalpy of fusion, which is, as we're told here, 6.02 kilojoules per mole. So that's going to give us 1.67 kilojoules. All right, so it requires 1.67 kilojoules of heat to melt 5 grams. That's our second segment. And then we just keep going through the rest. So segment 3, now we're in liquid water at 0 degrees Celsius, and we're going to warm that from 0 degrees Celsius to 100, which is the next phase change temperature. So in this segment, we're dealing with liquid water, so the heat is just mc delta T for the liquid phase, which we've used this heat capacity many times in calorimetry problems and other things in Chapter 7. So we have 5 grams of water. The heat capacity for liquid water is that familiar 4.184 number. And in this case, we're warming it by 100 degrees Celsius because we're going from 0 to 100. So it's a temperature change of 100 Celsius or Kelvin, however you want to think about that. So that's going to be 2,090 joules, which is 2.09 kilojoules. We'll keep them all in the same units. So remember, at the end, we're going to add all these together. So we're going to calculate the heat for each segment and then add them all together to get the total heat. They have to be in the same units, either joules or kilojoules. All right, segment 4 is going to be the phase change going from liquid to gas. That's boiling the water or vaporizing the water. And again, for any phase change, the heat is just going to be the moles of that substance times the delta H for that phase change, which in this case is vaporization. Okay, so make sure we use the correct value here. It's vaporizing now, going from liquid to gas. And so again, we have 0.278 moles of water. We calculated that. We're not gaining or losing any substance here. And then the enthalpy of vaporization is 40.7 for water. And so that gives us 11.3 kilojoules. One thing we should notice, we haven't really talked in detail about this, the enthalpy of vaporization is much larger than the enthalpy for fusion. So we can think about why that is based on other things we've learned in this chapter. So fusion is melting a substance. You're taking a solid into the liquid. You have to break some of the intermolecular forces to sort of disrupt that solid phase regular structure, but you still have a lot of contact between the water molecules, still a lot of hydrogen bonding. But when we boil something, we have to break all of the intermolecular forces, separate all the atoms or molecules into the gas phase, so it typically takes a lot more energy to vaporize something than it does just to melt it. All right, so that's a common trend you'll see for just about every substance, is that vaporization enthalpy is significantly larger than the enthalpy of fusion, because for vaporization you have to break every single intermolecular force. All right, and then finally the last segment is going to be heating the steam from 100 degrees Celsius to the final temperature, which is 140. All right. So now we have gas phase water, which we call steam. And as we say in this problem, we're taking it all the way up to 140. So we start at the phase change temperature, which is 100, end up at 140 degrees Celsius. Because we're in a single phase of matter here, we're not doing a phase change. It's just going to be the mass times the heat capacity for gas phase times delta T. So we have 5 grams of steam. The heat capacity for the gas phase is 2.00. And in this case, the temperature change is 40 because we're going from 100 to 140. So that comes out to 400 joules, which is 0.4 kilojoules. And then finally, the total amount of heat that we've added to do this transformation is going to be the sum of all of them. So 0.209 kilojoules, which was warming the ice to its phase change temperature of 0. 1.67 kilojoules, which was required to melt the ice. 2.09 kilojoules, which was required to warm up the water to 100. 11.3, the biggest contribution, is for vaporizing the water. So remember, it takes a lot of energy to vaporize something, so that's very often going to be your largest term. All right, there we go. 11.3 kilojoules, and then finally the last segment was 0.4 to warm up the steam. In total, we get 15.7 kilojoules. All right, so it's really just two types of calculations you have to do: MC delta T for a single phase, and then moles times enthalpy of vaporization or enthalpy of fusion for the phase change. And you just add up all those together depending on how many of them are important. All right, so that's the only example I'm going to do for that. There's a lot of steps there, but none of them are particularly difficult. What we need to move on to now is the last thing we're going to talk about, which are phase diagrams. So we've mentioned a lot about the effect of temperature on phase changes. We know that as we just saw, as you warm up a substance, you go from solid to liquid to gas. So we know that the phase that exists is dependent on temperature, but it's also dependent on pressure. So, you know, those normal boiling point and normal freezing point for water, 0 degrees, 100 degrees, that applies to when you have 1 atmosphere of pressure surrounding that water. But if we go to a much different pressure of the surroundings, either higher or lower, the phase change value, the phase change temperatures change. So what a phase diagram tells us is it summarizes all of that information, all the information related to the temperature at which a certain phase exists and the pressures at which those phases exist for any given substance. So the definition of a phase diagram is it's a temperature-pressure diagram. So those are the two axes. And it shows us the condition under which each phase exists, the conditions of temperature and pressure specifically. All right, because the stable phase for a substance is going to depend on both of those, temperature and pressure. You could get the same information no matter how you plot it, but conventionally the y-axis is going to be pressure and the x-axis is going to be temperature. All right. This is just how the powers that be decided to do it. And so we're going to follow their whims and do it this way. Pressure on the y-axis, temperature on the x. So then the regions for a phase diagram are the phases of matter for that particular substance, which are typically going to be solid, liquid, and gas. There are some substances that have multiple solid phases. Now what does that mean? And how do you have two different phases that are both solids? Now that's where if you have, as we talked about, these crystal structures, let's say you have a metal that exists as a cubic crystal structure at one set of temperature and pressure, perhaps in another set of conditions it will exist as a hexagonal structure. So there are a lot of compounds, as you change the temperature and pressure, the crystal structure changes. So it's still solid, but it changes to a different type of structure. So sometimes in a phase diagram, we'll see one example of this today, you'll have multiple regions that both correspond to solid phases that just have different structures, but are still both solids. Now the question is, why are these useful? Because it allows us to predict phase changes under a bunch of different conditions. So especially if any of you become chemical engineers, phase diagrams are very important for a lot of stuff that they do. You can predict vapor pressures and many other properties as we'll get into. All right, so it's useful for both synthesizing materials. It's useful for using them in chemical reactions in some cases. There are a lot of different things you can learn from a phase diagram that are helpful in the world of chemistry and chemical engineering. All right, so let's look at a phase diagram for water to understand how this works. So we have, as I said, pressure on the y-axis, temperature on the x-axis, and what these lines represent are going to be phase change lines. So these are the conditions under which two or more phases exist simultaneously. So as you go along, as you cross over one of these lines, you're going between two different phases. So the regions are always going to be, in the sort of left side you have the solid. So if you're under any of these conditions of temperature and pressure, you're going to exist as solid water, which we call ice. The middle part is the liquid phase. And then over here, high temperature, low pressure is gas. Now hopefully these regions make a little bit of sense to us. So we know that as we go to the lower temperature side, we expect that to be solid, and as we go to the higher pressure, that's going to compress any liquid into a solid. So low temperature, high pressure is going to be solid, liquid's kind of in the middle, and then gas, as you go to higher temperatures and lower pressures, that's when it tends to exist in the gas phase. So those are the three regions for the phase diagram: solid, liquid, gas. And then the different lines and different points on the diagram can kind of tell us some things. So I'll highlight these in some different colors as soon as I'm allowed to. There we go. All right, so this line here, as I said, when you have a line that divides the phases, this is the solid liquid line. And this allows you to predict the melting point at different pressures. Okay, so that's the solid liquid line, and then we also have this other phase change line, which is, I'll show in green here. This is the liquid gas line, which allows you to predict boiling point as a function of pressure. Okay, so as soon as anywhere on this line is where we're able to boil the substance where the liquid and the gas coexist or interconvert. All right, so that gives you the boiling point at different pressures. And then some things we can get off is we'll get some more information on the next slide here. Remember that normal boiling point and normal melting point correspond to 1 atmosphere. So if we're at 760 millimeters, which is 1 atmosphere, and we go straight across, the place where we cross the solid liquid line is the normal melting point, which we see is 0 degrees Celsius. And the place, so that I'll label that A, that's going to be our normal melting point, which is the melting point at 1 atmosphere. All right, so we already know that that's 0, and that's where it is on the phase diagram. You go to 1 atmosphere, You find where that intersects temperature and the solid liquid line. And then if we go across to the liquid gas line, that's going to be the normal boiling point, which is this point here. And we see that that corresponds to 100 degrees Celsius. I'll call that point B. All right, now we already knew those values for water, but now what we can do is we can predict boiling points and melting points for other substances, and we can predict them at other pressures. So if we drop the pressure, we see that the melting point changes a little bit, the boiling point tends to change a lot as a function of pressure, kind of what we talked about last time. So it allows us to predict those in a very graphical format for a bunch of different conditions. All right, so that's an introduction. Now what are some other things we can learn from this? A little bit more details now, so just a smaller version of the exact same thing I just showed you. So one thing we notice that we can look at is what's the slope of the liquid solid line. The liquid solid line can either have a negative slope, which we have here, or it can be positive, which we have for other substances. In this case, it's negative. So let's think about what happens. If we start at some value here and we increase the pressure at the same temperature, we notice that we cross from solid into liquid. So as we increase the pressure, we go from solid to liquid. And so when you have a negative slope, that's what happens in this case. Increased pressure converts from a solid to liquid. And what that means for us is that the liquid is more dense than the solid. All right, because as we increase the pressure, we're packing everything together more, and eventually you get to a pressure where it goes from liquid to solid. So that means this, from solid to liquid. So that means the liquid is more dense. All right, and this is not typical for most substances. Water is kind of a weird one in this regard. So as we increase the pressure, we go from solid to liquid, which means the liquid is more dense than the solid. Okay, because it comes in at higher pressure. And we know that for water that's true. If you have a glass of ice water, the ice floats on top of the water because it's less dense than the water. And the phase diagram allows you to predict the relative densities of the phases. So as you increase the pressure, you're going to a region of higher density. And in this case, that goes from solid to liquid, so liquid is higher. We also have this point here called the triple point, which is where all of these lines intersect. All right, so we have this point here. It's labeled O, and I'll call it X just to make it a little bit more obvious. And that's the point at which the solid, liquid, and gas coexist. Now, that doesn't occur at 1 atmosphere, so we don't have that triple point doesn't occur under normal atmospheric conditions, but at lower pressure, which is labeled here as 4.579 millimeters, you have a temperature at which the solid, liquid, and gas coexist. And under these conditions, solid and liquid have the same vapor pressure. All right, and then finally there's one other point in the diagram called the critical point. So as you'll notice, our liquid gas line sort of just ends. It just kind of, there's just an end to it. So that's what we call the end of that line. It's called the critical point, which I'll label with a Y. And that's the point at which the vapor can no longer be liquefied, or vice versa. So basically, once you get beyond this triple point, you no longer have distinct liquid and gas phases. Remember, this lower one here is gas. So the point at which the vapor can no longer be liquefied is called the triple point. That's the end of the liquid gas line. So beyond this point, the liquid and vapor phases are indistinguishable. And it exists as what is called a supercritical fluid. All right, so once we get to this temperature and pressure way up here, we no longer have distinct liquid and vapor phase. We just have one phase that we call supercritical fluid that in some cases has properties of both liquid and gas. It's kind of a weird one. We don't have a lot of experience in real life with supercritical fluid because for water you have to go to very high temperatures and pressures to see that. There is, for carbon dioxide, supercritical carbon dioxide is accessible at sort of normal temperatures and pressures. So a lot of people started using supercritical carbon dioxide for some certain chemistry applications, but it's basically just a fluid that's neither a liquid nor a gas that exists beyond the critical point, which we call the end of the liquid gas line. All right, let's look at one other example of a phase diagram, this time for what I just talked about, CO2. And this brings in a new concept called sublimation. So if we label the parts of this diagram, we have solid, liquid, gas, just like we did before. And then a couple things we notice. Let's make this. In this case, the pressure is in atmospheres on the y-axis. It's actually bar, but atmospheres and bars are almost identical, so we'll call it atmospheres, which we're more familiar with. So if we're at 1 atmosphere, one thing we notice is that as we warm the substance at 1 atmosphere, we go directly from solid to gas. The liquid phase doesn't exist below 1 atmosphere, really below, in this case, 5.2 atmospheres, which the triple point is. So liquid phase doesn't exist except at much higher pressures. So at normal pressures, when we go and raise the temperature, we go directly from solid CO2 to gas phase CO2. And you guys probably know what dry ice is. That's exactly what's happening there. Dry ice is frozen CO2, but at normal atmospheric pressure, you don't go through liquid CO2. You go directly from solid to gas, and we call that sublimation. All right, so most substances can sublime under certain conditions, usually lower pressures, but for CO2, it sublimes at normal atmospheric pressure. So sublimation is the process of converting a solid directly into gas, skipping the liquid phase. And so we notice that at 1 atmosphere, CO2 sublimes at minus 78.5 degrees Celsius. That's that temperature right there where it hits the x-axis. All right, so dry ice, as we know, is very cold and it has to be minus 78.5 or below, or else it'll start subliming into the gas phase. And if you ever leave, a cooler of dry ice sitting for too long, it'll come back and there's nothing there because that's just the gaseous CO2 going everywhere. All right, so this solid gas line here, those are the conditions under which we can have sublimation. As we cross that line, that's another line that we have that refers to sublimation. The other thing we'll notice about this one is that in this case, the solid liquid line has a positive slope. All right, so this is our solid liquid line. If we start at some temperature and pressure in the liquid phase, if we increase the pressure straight up, we go into the solid phase. All right, so in this case, we have a positive slope for solid liquid line. And that means the solid is more dense than the liquid. All right, because as we increase the pressure, we're going to higher and higher density, and as we do that, we cross from liquid into solid when the slope is positive. Okay? So that's just a very similar one to water, but we have a couple additional features here that are a little distinct. Another one I'll show you is for carbon. This is one where we do have, as we know, 2 different solid forms. So we've already talked about how carbon has 2 commonly occurring allotropes, diamond and graphite, and the phase diagram shows that. All right, so we're not going to expect you to know how to label these types of diagrams off the top of your head, because this is a more complicated one, but we still have some similar features. So gas is going to be lower right, and you have carbon in the gas phase that requires very high temperatures and low pressures. Sort of the intermediate point here, higher pressure but also higher temperature, is going to be the liquid part. So in this region you have liquid carbon. And then we notice that on the left side of the diagram where you have the lower temperatures, you have two different phases. You have another phase change line here. And so that's going to be the two different solid phases. Graphite exists at lower pressure, and then diamond is at higher pressure. All right? So we do notice that these are very high pressures, 10 to the 7th. This is pascals now. They all have different units, which is annoying. It's hard to find phase diagrams that all have the same units. But these are going to be, hundreds of atmospheres basically that we're working with here, pretty high pressures. But so if we go to really low pressure, we notice that graphite is the stable phase of carbon at low pressure. So when diamond exists, it's what we call a metastable phase, where yes, we can have diamond existing at atmospheric pressure, but over some long period of time, diamond will convert to graphite. But as we talked about, it's very long time, millions of years probably. So at very high pressure, though, and we see that it's greater than 10 to the 9th pascals. That's where that phase change line starts. So 10 to the 9th pascals is about 10 to the 4th atmospheres or so. So about 10,000 atmospheres, pretty high. And at that point, graphite converts to diamond. So there are synthetic diamonds that people make where they take graphite or some other form of carbon and they press it to 10,000 atmospheres, whatever it requires to get to that, and you can actually convert graphite into diamond. Now it doesn't look nearly as nice as the naturally occurring diamond, so none of the bling that any of you guys have is going to have the fake diamonds are all going to be naturally occurring ones that you mine out of the ground, but you can make diamonds from graphite if you go to really high pressures. So that's what the phase diagram tells us. All right, so what we're going to close with are just a bunch of example problems using a phase diagram, and just to get an idea of the types of questions we can ask you about phase diagrams. All right, so we have this phase diagram here with a bunch of points labeled with different letters, and the types of questions we'll ask you is we'll show you a phase diagram, we'll give you some conditions of temperature and pressure, and then ask you something about that. All right, so we have which phases is or are present at point A. So point A is here in the diagram. And remember that for a typical phase diagram, the three regions are we have solid over here, we have liquid in the middle, and then gas in the lower right. And so at point A, we're in the region where only the solid exists. So when you're on a phase change line, you're going to have two phases, but if you're completely in one of the regions off the line, which point A is off the line, there's only one phase, which is going to be solid. All right, you notice that point A is a little bit to the left of the solid liquid line, so at that temperature and pressure, you're only going to have solid for whatever substance this is. This is a totally fake phase diagram. It's not a real substance, but it allows us to see how these questions go. All right, so next one, which phases is or are present at point B? So point B is here. It's always helpful to label the diagram. Solid, liquid, gas, same diagram, same as before. So we notice that at point B, we're in between. This is the line that intersects the liquid and the gas regions. So we're on the liquid-gas line, which means liquid and gas both exist under those conditions. All right, so in other words, point B tells us the boiling point of this substance when we're at whatever pressure that is, about 0.9 atmospheres. All right, so some more information we could get from this. Point B is 0.9 atmospheres. It's about 200 Kelvin, so that means the boiling point of this substance at 0.9 atmospheres is 200 Kelvin. So when you go to the liquid gas line, you can predict the boiling point at any pressure by finding out where it intersects that line. Okay, so that's the liquid gas line. So both phases exist under those conditions. All right, next is a multiple choice one. Which temperature and pressure are closest to the triple point? All right, so remember the triple point is where solid, liquid, and gas all come together, all intersect. So it's where those three different phase change lines all meet. So that's going to be right there. It's where all three of them come together. We want to find which temperature and pressure are closest to this. So we go down to the temperature axis, and that's between 100 and 150, so around 120. And then the pressure, if we go over to the y-axis, is 0.6 atmospheres. All right, so the triple point for this substance, triple points are always defined by a temperature and a pressure. It's 120 Kelvin, 0.6 atmospheres. You find where exactly that intersection is of those three phase change lines. So that's going to be choice A. Now, the other thing that the triple point tells us, which is an important consideration, is that when you're at a pressure that's below the triple point, you're never going to have the liquid phase existing. So we notice that a triple point occurs at 0.6 atmospheres. If we draw a line all the way across 0.6 atmospheres, this liquid region exists entirely above that pressure. So you're never going to have liquid below the triple point. That's another important feature of the triple point. When you're below that pressure, the liquid phase can't exist. So that's another thing we could ask you about this type of diagram. All right, moving along, continuing to see some more things about this and eventually start beating the dead horse. So what are the normal melting and boiling points for this substance? Okay, so remember that normal, as we talked about last time, corresponds to when you have the atmospheric pressure of 1 atmosphere. So at the normal melting and boiling points, the pressure has to equal 1.0 atmospheres. All right, so remember that what we're going to do to find the melting point and the boiling point is we're going to find where do those phase change lines occur at that pressure. So we're at 1 atmosphere, we draw a line straight across. All right, so the melting point is going to be where solid and liquid, where it crosses into the solid liquid region. So the melting point is going to be this point here, which I'll label with another letter X. And we take that, we extrapolate that down to the x-axis to find what temperature that corresponds to. You have to use your eyeballs a little bit, but it's going to be around 110 Kelvin. Okay, so the melting point, the normal melting point at 1 atmosphere is 110 Kelvin. You go down to the x-axis to find that. And then for the boiling point, which I'll do in a different color just to keep them distinct. All right, so for boiling point, we want to find where the liquid and gas line occurs. So that's going to be right here. We stay at the same pressure, 1 atmosphere. We find where that 1 atmosphere crosses the liquid gas line. We go down to the x-axis to find what temperature that corresponds to. And so this point Y, as I'll label it, is going to be the boiling point, at the normal boiling point specifically, which is around 220 Kelvin. Okay, so as I said, we can read off melting points and boiling points at any conditions of pressure. If we ask you specifically for the normal boiling or the normal melting point, that means the pressure is exactly 1 atmosphere. All right. Any questions so far? All right, let's see what's next. A few more. All right, we want to know what is the sublimation temperature for this substance at 0.4 atmospheres. So remember that sublimation means going directly from solid to gas. So 0.4 atmospheres is right here. This is solid, liquid, and gas, as we already labeled every time. So going directly from the solid to gas occurs right at that temperature there. We go down to the x-axis, and that's going to be 100 Kelvin. All right, so that's the sublimation temperature. Another implication of triple point is that sublimation only occurs below the triple point. Once you're above 0.6 atmospheres, you always go from solid to liquid first and then gas. So sublimation can occur at any pressure below the triple point. Here at 0.4 atmospheres, that would be 100 degrees or 100 Kelvin. Right? All right, so another type of question we can ask you is a little bit more involved. So let's say you're in a lab and you start with the substance at 0.2 atmospheres and 100 Kelvin. So that's going to be starting right here. And then you increase the pressure to 2 atmospheres while maintaining a constant temperature. Which of the following lists the phases that will be encountered during this process? So we're starting here and we're raising the pressure without changing the temperature. So we're basically going on a vertical line through our phase diagram. So we're going to follow this vertical line here. We're starting at 0.2 atmospheres, we're ending up at 2 atmospheres, so we're going to go up to this point here. All right, so that's the process we're doing. We're raising the temperature while staying at constant, we're raising the pressure while staying at constant temperature. So we're drawing a vertical line in our phase diagram. So we're starting down here in the gas region. So that's our starting point. This initial point down here is in the gas region of our diagram. When we go to this point here at 0.4 atmospheres, then we're going to get to the solid. Remember that 100 Kelvin is a sublimation point. So at 0.4 atmospheres, we cross over into the solid region. That's this region here. So then we travel through the solid region of our diagram, and up here at about 1.6 atmospheres, as we raise the pressure above that, we go into the liquid phase. So this is another situation where the liquid is more dense than the solid, and as we raise the pressure, we go from solid to liquid. So we encounter all three phases as we go from low pressure, 0.2 atmospheres, up to 2 atmospheres while maintaining 100 Kelvin as the temperature. In the order of the phases, we start with gas, then we go to solid, then we go to liquid. So the correct order is going to be choice D. Gas, then solid, then liquid. All right, so that allows us to look at how the phase changes as we raise the pressure over a large range. All right, and as we talked about on this problem, what are the relative densities of the solid and liquid phases? All right, so we look at the slope of the solid liquid line, which is this line here. That slope is a negative value, and that means as we start in the solid part of the diagram, somewhere here, as we raise the pressure, as we showed you, you go from solid to liquid. So raising the pressure corresponds to an increase in density, which means that the liquid is greater than solid. All right, because as we go straight up vertically, we cross from solid into liquid. That means that the liquid is more dense than the solid because it occurs at higher pressure. All right, so that's going to be choice B in this case. All right, questions on that concept or anything else so far? All right, we're almost at the end, I promise. We got a few more, just giving you the variety of things we can ask you. All right, so another concept that comes out of phase diagrams is vapor pressure. So if you want to know what is the vapor pressure of this substance at 250 Kelvin, so the last one, good. All right, so the vapor pressure is going to be, the way we find that is we take the liquid gas line. So we're going to follow this liquid gas line. We're going to find out the pressure that corresponds to 250 Kelvin. So when you're on the liquid gas line, the pressure that you read off of this line corresponds to the vapor pressure. So if we're at 250 Kelvin, we go 250 Kelvin, which is here. We take this up to the liquid gas line. And then we extrapolate that over to the pressure axis. So any pressure that intersects the liquid gas line corresponds to the vapor pressure. So the vapor pressure in this case is around 1.2 atmospheres. All right, because this tells us the temperature. Remember, this tells us at which the substance goes from liquid to gas. So that corresponds to the vapor pressure because boiling occurs when the vapor pressure equals the surrounding pressure. So if the temperature is 250 Kelvin, the vapor pressure is 1.2 atmospheres. We read that directly off of this liquid gas line. All right, that takes us to the end of all the new stuff. We have a bunch of review for the next week and a half, and I'll see you later today at the review if you're able to come.